Hello everyone and welcome to Treble's flagship event of the year, where we are introducing a major evolution of our platform, as well as showcasing some really interesting new research findings and featuring great guest speakers from the industry. Before diving in, I would just like to thank the audio and acoustics community for their general interest and support of Treble, but also of this particular event. We have more than 1,000 people that signed up here today, so thank you all for being here. I think that number alone says something about how exciting and growing the field of audio AI and simulations and acoustics is. Now, I'd like to start by zooming out a little bit and providing a bit of motivation for today's event. We are really living through a fundamental shift in how people are interfacing with machines. Voice is becoming a primary interface. Moreover, there's an explosion in wearable devices, smart devices, robots, autonomous systems, where sort of sound is a central component. And finally, I'll mention audio as a sensing modality for physical AI is really a growing topic. So all of these exciting technological progresses are powered by AI or machine learning, but machine learning systems have all in common that they need high quality data. Not just more data, but repeatable, scalable, accurate data from real world conditions. And this is exactly where a lot of teams struggle. Collecting real world data from the real world is time consuming, it's slow, and it's expensive. It's fundamentally unscalable. And this is exactly what we have been building the Treble SDK to address, to overcome this data bottleneck and to be the simulation and data layer for audio AI development and acoustic virtual prototyping across industries. The SDK has been on the market for 1 year now, and we've been over the moon with the reception and the amount of usage over that time. We have many leading tech and AI companies, consumer electronics companies, automotive companies, voice companies, startups, researchers using the SDK to improve machine learning models, to accelerate their development cycles, and improve all kinds of products as well. So thank you for that. And today we are introducing a major evolution of the SDK. We're going from it being a powerful simulation tool to being an end-to-end audio AI development and virtual prototyping platform, spanning data, physics-based simulation, and machine learning native workflows. In other words, sort of data curation and augmentation, feeding into machine learning training pipelines or product prototyping pipelines, and then doing testing and evaluation, all in a seamless virtual process within one system. So that's sort of the big picture view that we are presenting here today. Now, as for the agenda for today, we have divided it into 4 main blocks. The first block is about using the Treble SDK to create acoustic data, to create virtual acoustic scenarios, spanning realistic environments, materials, devices, and so on, setting up thousands of scenarios like this and simulating them with high precision using our proprietary simulation technology. And under this block, we'll introduce a lot of new features, especially this notion of being able to now, for the first time, simulate dynamic scenes where sources can be moving, people can be moving, listeners, and so on. And it is really a world's first capability to be able to simulate this with precision and at scale. We'll also introduce great new features around device modeling and near-field acoustics or own voice phenomena, and so on as well. The second block pertains to the fact that not all teams have the bandwidth or the willingness to create such data themselves. So now in Treble, we are introducing the ability to simply access directly pre-made, curated, high-quality acoustics data sets made by the Treble team. Under this block, we'll also introduce a lot of new features for large-scale data workflows, for curating data sets, filtering them, manipulating metadata, and then feeding it into downstream pipelines. The third block is our research spotlight. Our AI research team has been investigating the relationship between data quality and downstream machine learning performance across numerous different use cases, and they show very unequivocally that better data leads to massive downstream performance improvements. In single channel speech enhancement, 0.2 PESC in their study, improvement In multi-channel speech enhancement plus ASR, they see a 30% word error rate reduction. Direction of arrival studies showing a 36% accuracy improvement. Source distance estimation showing 51% accuracy improvement. So these are not marginal improvements, but substantial improvements, proving the sort of data hypothesis that better data means better performance. And finally, in the fourth block, we sort of bring it all together, the acoustics data and input data from audio, from speech and noise and so on, and show a lot of new tooling for setting up virtual audio scenes, controlling conversations, turn-taking, dynamic, signal-to-noise ratios at scale, and visualizing all of this, and then again feeding that into downstream pipelines. In addition to all of this, from the Treble team, we have, as previously mentioned, amazing guest speakers. We have Eric from Hugging Face talking about the audio AI ecosystem and about our collaboration between Treble and Hugging Face. We will have Tim from ai-coustics talking about their great work in speech enhancement and voice AI. And finally, we'll have Yauheni from GN Jabra talking about product development and algorithm development using simulations. So really exciting talks. And yeah, just without further ado, I think we dive into it. I will mention that we have pre-recorded deep dives of the different sections here. We'll send those to you afterwards. So if you want to dive deeper into specific topics, you can do that then. But we will keep this webinar within 1 hour plus Q&A, live Q&A at the end. So without further ado, let's go into the first block, which is about creating virtual acoustic environments using Treble. Now we dive deeper into using the SDK for running high-fidelity acoustic simulations. This is the area the SDK has been focused on up until now, but today we're introducing a lot of new functionality in this regard. Later in the webinar, we will then show sort of an expansion of the platform, both in the sense that you can now directly access curated high-quality acoustics datasets within the SDK, and a lot of new functionality for downstream processing of the acoustics data. Now, when it comes to running acoustic simulations, there are sort of 4 main pillars to that work. Number 1, we need to define some 3D environments. Number 2, we need to assign some materiality to those environments. Number 3, we need to put some sound sources into the environments. And number 4, some listening devices or receivers as well. This input data is then fed to our proprietary physics-based simulation engine, which simulates both with very high precision and high efficiency the acoustic propagation in those environments, taking into account all the complex materiality and loudspeakers and microphones and whatever you put in there, and you get back results which are exactly comparable to what you would get from a real-world measurement scenario. And we have validated the accuracy of the engine across numerous different benchmark studies, which can be found on our website. Finally, I'll mention that typically you will want to do this kind of work at scale. Of course, you can manually curate one particular scenario and simulate that, but oftentimes we want to create thousands of representative scenarios, and we want to be able to both set them up and run them very efficiently with little effort. And there's a lot of tooling in the SDK for that as well. Okay, let's walk through the 4 pillars in the SDK, bring it together in an example case, and also say a few words about doing this at scale. The SDK comes with a very large database of 3D environments that you can leverage for your work, spanning apartments, restaurants, classrooms, meeting rooms, and much more. We see a couple of examples here on the screen, a multi-room apartment and a very large restaurant. You can also programmatically create 3D environments. If you want to create random environments, you can include furnishing and complex shapes and so on. Again, we see a couple of examples here on the screen when doing that. You can, of course, also import 3D environments from a variety of CAD, BIM, USD formats, and so on. For materials, we have a very large database of materials that you can use. You can either assign them very specifically on different surfaces, or you can use our new functionality, which is LLM-based, where you can essentially give it a prompt and it will assign reasonable materials based on your prompt. Putting, glass on the window, wood on the table, carpet on for reasonable materials. For sound sources, I'll a lot of advanced functionality here. You can model directional point sources. Here I'm showing an example directivity of speech from our directivity library that's very commonly used. You can also use what we call surface sources or velocity sources, where you can import the CAD of your particular source or loudspeaker and excite the membranes. That's a very accurate approach where you can model near field phenomena, place it on a table or close to a wall and so on, like we see here, the soundbar under the TV. Now, a major new thing that we're introducing today is the ability to have moving sources and moving listeners. This is something the industry has been eagerly waiting for, and we're really excited to put it out to the world. It's really a world's first capability to be able to model with high precision and at scale this level of dynamics where you can have movement, changing the orientation, and so on. And I think this really opens up a lot of new opportunities for data generation and acoustic virtual prototyping. And we have lots of tooling for making it easy to create trajectories and so on along with this. Finally, the fourth pillar, listening devices. You can model very complex multi-mic audio devices in the SDK. You can essentially inject them into the 3D environments in post-processing after you've run the acoustic simulation. That's a very efficient way to create device-specific data. Now, the device properties themselves, you can either simulate them in Treble. If you have a CAD of your device, we see an example here of AR glasses mounted on a mannequin, but you can of course also import these properties if you like. Now let's look at it together in a case study. In this example case, we're again going to work with a smart glasses audio device. What we're seeing here on the screen is our new device importing UI and associated workflow, where the goal has been to try to make it as easy as possible to import such complex audio devices. For example, there's tooling showing you whether you have appropriate level of simplification in your geometry, as well as ability to point to where in the geometry you might have issues or where you should focus your sort of simplification efforts if needed. A new thing as well is this concept of what we call a source receiver device. So a device that's both a kind of a loudspeaker and a listening device in one go. That allows you to run very efficient near field simulations, and then you can of course combine that with far field simulations as well, where the sources are further away. Now let's put this guy into an acoustic scenario. What we're going to do here is create a bar scenario. So you can see here the bar, there's a couple of moving sources in here. The bartender is moving. There's a guest that walks through the space as well. There are a bunch of other guests sitting around the tables. There's a sound system in the ceiling. And then, of course, the guy himself is in here along with his group of friends. They're talking here. And we can then obviously simulate this with very high precision, what exactly these microphones on this device will pick up, both from the own voice and from all the different sound sources that we have in that space. And if we look at a couple of example results, first thing I'm showing here is the device-specific room impulse response from the mouth source and to the microphones, the 5 microphones on the glasses. Here, of course, the direct sound is very strong, but there are still reflections here in the later part of the signal. Another example here is one of the friends talking, where the direct to reflection ratio is different compared to the own voice. Of course, it's a source further away. We can then convolve this with audio data, with speech or noise data from all the different sources to construct a virtual audio scene. We'll talk much more about that later in the webinar today. Now, the SDK lends itself very naturally to setting up acoustic simulations in bulk or at scale, it being a Python-based programmatic interface. There are many ways to go about that, but here's one simple example just to show an example. In this scenario, we are setting up 5,000 living room scenarios. In each one of them, we have 3 sources and 3 listening devices. We define some rule sets around where we place those sources and receivers, what kind of material assignment we do, and so on. And then just in this short for loop, we're really doing all the setup needed to create all of these acoustic scenarios define the simulations, set the simulation settings, and so on. Here we then plot the first 5 environments or simulation scenarios. We can see some variation in the geometry and materials and sources and receivers and so on. And then to run all of this, we would simply run project.start simulations. Everything gets shipped to the cloud, run in parallel, and you get back your data very quickly. That was it about creating acoustics data with the Treble SDK and running high fidelity simulations. Now let's give the word over to Eric from Hugging Face.
Hello everyone, my name is Eric. I'm an audio ML engineer at Hugging Face, and I've got my friend Richie here. Say hi, Richie.
Hey there, Eric and everyone. Great to meet you all. Let's make this fun.
All right, so I'm passionate about open source, and so is Richie here. And with Hugging Face, our mission is to democratize open source AI. And that could be models, data sets, and tooling, and just make it easy to use for the community so they can build awesome products and tools. So my focus at Hugging Face is in audio, and in the last few months we've been working with Treble on open sourcing a data set, which I'll mention a bit about later, but also helping them flesh out some really cool new features in their SDK. And so I'll share a bit about that and what we're excited about at Hugging Face and about this collaboration in general. How does that sound, Richie?
Sounds fantastic, Eric. I'm all ears. Well, figuratively.
So a bit about Hugging Face, in case you're not familiar with us. So the company was founded in 2016, initially for building chatbots, but expanded past that when the original team saw that the tools that they built could benefit others. And the mission has become now to democratize good machine learning through open source and through open science. And so there's many reasons why you may want an open source versus a closed source. Could be for security reasons, customization, transparency, cost, latency. So what's nice about open source models is that you can run it fully on your machine. You can choose how you run it. You can control how the data goes in and out of it. So those are some of the advantages, but you don't get some of maybe the pros of closed source models where there's just a single endpoint cloud API that you use. And there's companies that adopt both approaches. So you have companies like us, which are really focused on the open source, and others who may prefer, or even clients who may prefer a closed source, ready-made, convenient solution. So around tooling, Hugging Face, we try to build a lot around this to help the community. So we have over 30 libraries to empower AI development and advancement when it comes to building applications with AI. And our main entry point is the Hugging Face Hub, which is a platform for building, sharing, and deploying AI. And that could be models themselves, data sets, apps, blogs, which can be shared on the hub, courses. So these are some courses that we've developed, and also benchmarks, so leaderboards, which we develop, but also some that are developed by the community. So really you can think of Hugging Face as this entry point into just so many resources for open source AI. And at Hugging Face, we try to provide resources for really at different entry points. So it could be in the data sets, if you want to train on a specific open source data set or maybe evaluate on it, providing models which engineers can either fine tune or use as is in inference, or through Hugging Face Spaces, you can host applications directly on the Hugging Face Hub and even have access to GPU compute through the Hugging Face Spaces feature. So specifically on audio, we have several initiatives related to audio at Hugging Face. So coming back to the hub, there's all sorts of models that you can find, many models that you can find on the Hugging Face Hub. When it comes to speech recognition, there are around 27,000 that you can find from established companies, startups, but also from academics. On TTS, so text-to-speech, you can find around 4,000 models to play with, to customize. And as I mentioned, there's also all sorts of data sets. So with regards to audio, there's 26,000 data sets that can currently be found on the Hugging Face Hub. And here I have a little screenshot of some of the demos that you can find on the hub. So a lot of them have to do with TTS or ASR, for music generation as well too. So I encourage you to check out huggingface.co, and you can find models, data sets, and also all these apps related to audio, but also to many other applications. As I mentioned before, we have several courses, one of them being the audio course, which was started a couple of years ago. And this really tries to get people familiar with audio ML, but also audio signal processing from the basics. So we learn about feature extraction, but then we also go further into building classifiers, understanding how speech recognition systems work, how TTS systems work, how you can fine tune them, and use all sorts of open source resources. So I encourage you as well to check this out. And it's also really a community-driven effort. So we're super happy for all sorts of contributions to material, to improvements for the course and whatnot. So down here, you can find the link for that. Another initiative that we actively maintain is the Open ASR Leaderboard. So this is a benchmark of both open source models, but also closed source models, such as APIs from companies like 11 Labs. So we've done a huge effort to aggregate over 70 models on this leaderboard, both open source and closed source, and evaluate them on a wide range of data sets. So you can get an understanding of which model works best for maybe which application or which type of data set, but also understand how their efficiency is, because we evaluate the models essentially on two criteria: word error rate, which is the transcription quality, and also RTFX, which stands for inverse real-time factor. So how efficient it is on a given set of audio. So yeah, I encourage you to check out the leaderboard. We also have a blog post where we compare the pros and cons of different types of models. And again, this is a community-driven approach. So we're super happy to have other models getting added, other data sets, other tasks. So currently we support English, but there's also multilingual. So you can test 5 or 6 different European languages at the moment. And on datasets, so here's a screenshot of one of the datasets that is available on the hub. What's really neat is you have these features such as playing audio, looking at the metadata without ever having to download the data. And here I actually have a screenshot of one of the datasets we released with Treble, a collaboration we did a few months ago, which I'll talk about in a bit. And on the side, you even have this kind of AI enhanced feature where you can ask natural questions about the data set to get some statistics on it. So it's a really neat way that through the hub, you can explore data sets without ever having to download them. And when you want to use them, a lot of it is enabled through the datasets library that's built by Hugging Face. So in our collaboration with Treble, as I mentioned, we started with this data set. So I encourage you to check out this blog post where we talk about it. So the data set itself consists of 10 furnished rooms, and there's 2 parts to it. One part is the room impulse responses, so that you can freely convolve audio with it as you like. And then there's convolved audio, prepared audio coming from the Libri speech test samples. And both of those sets have mono, single channel audio, 6 channel audio, and also higher order ambisonics. And this is a great data set for benchmarking, and we were excited to see how the community uses it. One feature that I find super exciting that Treble is coming out with recently is this tighter integration with the Hugging Face Hub. So after simulating certain scenes, certain impulse responses, they have this new feature now where you can upload those scenes, those impulse responses to the hub to share it with your collaborators, to share it with partners, and then they can conveniently download it from the hub with the data sets package from Hugging Face. So here you can see some of that workflow for pushing some impulse responses to the hub. And then here you can see how you can collect perhaps a noisy data set, which then you can convolve with an impulse response data set that's also been downloaded from the hub. So this is super exciting. And I think this is a great bridge between the advanced simulation, which the Treble folks are amazing at, and also some of the ML tooling that we've tried to enable through the datasets package, through the Hugging Face Hub, and any other training or evaluation workflow that some of the community may have. So this is a huge win for the community. I'm excited to see how people use this. So we're excited to continue working with Treble to make their realistic engine and the artifacts seamlessly work with modern ML tools and all the resources that are available on the Hugging Face Hub. As we've already seen in the last 10 years, realistic far-field data has been important for products such as smart speakers, and it'll continue to be important, especially for embodied AI and robotics, such as my friend Richie. Isn't that right, Richie?
Absolutely. That's right. Realistic far-field data is key for making smart speakers and robots like me even more effective and natural. It's exciting to see how this can help shape the future.
Thanks, Richie. Thank you, everyone.
Hi, my name is Daniel Georg Nielsen. I'm the product manager of the Treble SDK, and I'm super excited to talk with you today about our new features and workflows in the SDK, which we call collections. Collections enables you to work on large amount of data, but also organize it. So if you have a lot of simulations that are scattered all over different projects and so on, and you want to have a unified and traceable way of working with that data, then collections are for you. It enables you to combine multiple simulations into one data frame and then work with it and ship it to your colleagues if needed. It also addresses the issue of data handoff between different teams. Often we see that there's a dedicated simulation team in an organization working on setting up the simulations and running them, and then there's a different team that consumes it and trains different machine learning tasks for downstream applications. With the collections, we provide a unified interface where the two teams can work and extract data from the same data frame, ensuring easy handoff and so forth. Finally, we also recognize that people use the SDK not just because we have high quality impulse responses, but also it provides a traceable and easy way of setting up large data generation pipelines. One of the things that you would probably like to extract is spatial information such as source location, receiver location, distance between them, and so forth. Furthermore, you're probably interested in sort of acoustic parameters for the different environments that you're simulating. The collection features make it very easy to append this metadata to the data frame, which is then paired with this very specific impulse response that has been run. This information is then sent with the data frame so the team that uses the data can use this information when they train their downstream tasks. Finally, we understand that not all teams are ready to jump into acoustic simulations. That is why the collection feature also enables Treble as, you could say, you can view it as more as a data platform where you can not just simulate, but you can also simply fetch pre-made datasets run by dedicated engineers here at Treble, where quality assurance and rich acoustic environments is the top priority. You can, through the SDK, access these datasets and immediately start using them either in our scene generator, where you can create these rich acoustic scenes with speech and noise and your own device, or you can simply download the impulse responses and use it in your own data generation pipelines. So we're super excited about this. Let's dive into the details. So the first thing I wanted to show you is a brief intro to our pre-made datasets that you can now access in the SDK. So if I just go ahead here and list all the datasets, we see on the top here Treble 10, which is this free dataset available for everyone with a SDK subscription, which we made together with Hugging Face. And below that you have a lot of different datasets that you can access through the SDK. So for example, we have this Treble small, medium, large dataset, which was used to create the very good results that will be presented by Georg a little bit later in the webinar, where we saw good reductions in word error rate and a nice increase in PESC score. So if you're interested in a dataset, it's very easy to sample it in the SDK. So here I'm just sampling from the bedrooms dataset. I get 10 IRs out that I can analyze, convolve with speech, whatever I like basically. I'm just going to show you here a quick plot of one of the spatial room impulse responses so you get a feel for what a sample looks like. Okay, here we go. First 9 channels is plotted here, and you can view that frequency response and everything basically, and analyze it and convolve with speech. And then you can also plot the underlying room model, essentially showing the source and receiver positions that were used to create this exact data you're looking at. And then you can sort of judge if this is something that is for you. Straightforward to purchase datasets in the SDK. Here I'm just showing you for the Treble 10 dataset, basically it's for free. I can access it with 2 lines of code. Then you can see here the data frame with over 3000 IRs available to you. Next up, I would like to dive into a little bit more in how we actually work with these collections. I'm on a very big dataset, so let's go into that. So just to briefly introduce, the collections built on Parquet files and the Polars data frames, which means that it runs in parallel, it's memory friendly and super fast to search it. We pair this with the underlying simulation models and simulation results, which means that you can very easily append information to this data frame that comes from the simulations or the positions of your sources and receivers. This makes it possible to do fully customizable filtering operations on this dataset. So for example, if I want a certain distribution of reverb time or a certain distribution of clarity, I want to know what the distance is between the sources and receivers in the training examples I'm going to use, you can do this in a matter of seconds. This plugs seamlessly into existing machine learning workflows. We built some nice data loaders that can lazy load results on demand into your training machines, or you can simply plug this directly into our scene generator and use and consume these IRs to construct these audio scenes. So let me just give you a brief example how this looks like in the SDK. So I'm going to load this dataset with 1 million room impulse responses. Let's see how it looks underneath. Going from left to right, we see first the simulation information, some overall information about sources, receivers, the position of those, and then sort of going to the right, we see more and more information. I can add metadata to this, and it just takes a few lines of code. Here I enrich the collection with acoustic metadata of T20, C50, and early decay time. And I can also add information about line of sight between all of the sources and receivers in the collection. I can very easily visualize this dataset with our plot function that works in the collection. So here, for example, I'm viewing the source receiver distance between every source and receiver in the entire dataset. It's also straightforward for me to instead plot the reverb time for all these impulse responses. And similarly, I could plot the clarity index here. I'm just going to do that. Maybe I want to see how it works as a function of line of sight, where we see the clarity sort of falls off a little bit if there's broken line of sight, which makes sense. I can then also make a lot of subsets on this very large dataset. So for example, I can filter based on the source type. I can filter based on the environment. I can filter based on IR lengths and source receiver distance. Finally, I'm creating a Gaussian distribution here of the T20 for 100,000 IRs. I want them to be distributed around 0.4 seconds with a certain standard deviation. And lastly, I want to also create a uniform distribution of C50. Here I want 20,000 examples, essentially. So if we just plot these distributions, here I'm plotting the T20, the 100,000 examples of that, and then we get a nice bell curve here around 0.4. I can also plot my C50, and remember here we wanted a uniform distribution. So I'm just gonna load that in, and we see a nice uniform distribution here for 20,000 samples. One way to then continue to work with this dataset is then to upload this to Hugging Face. I'm just gonna do that here, a few lines of code. So here we create you can say a split where we want 80% of it to be for training and 20% to be for tests, and then we can push here to Hugging Face just in a few seconds, basically. And then another option to continue to work with the dataset, if you want to stay in the SDK, for example, use our audio scene generator, you can save it, the custom dataset like this, basically, and it can be accessed by you or anyone in the organization. Awesome. Thank you so much for tuning in. The Treble SDK is all about working on a large amount of data, and that's why we are super excited about bringing you this feature where you can filter and work with large amount of data and make it ready for whatever purposes you like. Thank you so much.
Hi, my name is Georg Götz, and today I want to show you the recent results from the Audio ML team here in Treble, and we want to show you why better data wins if you train neural networks in audio. So what we did is that we researched the relationship between simulation quality and neural network performance. Because right now the status quo in Audio ML is that people generate large training datasets, but they often use very simple simulations. So they either use only shoebox rooms or only uniform absorption, typically quite simplified source and receiver models as well. On the other hand, if you use the Treble SDK, we have quite many more new opportunities. So we can have advanced rooms with additional furniture in there, different scattering objects. We have a large database of different materials that can be used. And also we have advanced source and receiver modeling capabilities that you can use. And most importantly, we have a highly accurate physics-based solver which combines wave-based methods and phase-based geometrical acoustics. And the big question for us was now, do we actually get better performance when we train neural networks with such data versus other data? And we want to show this to you now with 3 models that we trained, a single channel and a multi-channel speech enhancement neural network, and then also one neural network that is doing binaural speech distance and localization. So let's start with the single channel speech enhancement. We trained DeepFilterNet 3, which works on mono recordings of speech, typically noisy speech in reverberant environments, as you can see here. And the neural network then outputs enhanced speech, where we have removed both the noise and the reverberation. In our experiment, we used the following configurations: that as the input, we used for the training the Microsoft Deep Noise Suppression Challenge. We used the speech dataset from there, the English subset to be specific, and we also used the noise files from there. And then when we think about the room impulse responses, we used two different datasets. The first dataset was used with image source simulations from the Habits image source simulator. And the second dataset uses treble room impulse responses. We trained for 30 epochs, and all of our samples were reverberated. We are mostly interested in the performance in real-world scenarios. That's why we always evaluate all of the three models on measured data. And in this case, we use speech from VCTK, and once again, the noises from the DNS4 dataset. And for RIRs, we use measured RIRs from the MIT and the ACE datasets. The training datasets we use, they cover quite a wide range of different acoustic conditions. So you can see here histograms of both the T30 and of the volumes. And those histograms show you the distribution of the treble dataset, but we tried to match as well as possible also the distribution with the other dataset. And now if we have a look at the speech enhancement performance, we use the perceptual evaluation of speech quality, in short PESQ, as an evaluation metric, which is a fairly standard evaluation metric in speech enhancement. And we can see here on the left side in gray, we have the performance of the image source model data. And on the right side, we have the performance of the treble data. And we see as soon as we use higher quality treble data, our PESQ improves by up to 0.19 in median values. We also tried to do a deeper dive there and try to figure out how does it look like at different signal-to-noise ratios. And here you can see at first now the signal-to-noise ratios for the image source model dataset. And we see as soon as you use treble data for your training, also there the PESQ improves a lot. But we also saw that the largest improvements were for larger signal-to-noise ratios. Now I want to continue with the multi-channel speech enhancement. So the big question is, why would we use device-specific multi-channel signals in the first place? And what we always have to remember there is that these signals have additional information compared to single-channel approaches. Because first of all, we have additional spatial information. So we have arrival times and phases at the different microphones. But then we also have additional spectral information that we get from interactions with the device, for example, reflections of it or diffraction, shadowing around the device, which is something that we see in the real world, of course, if we do measurements, but we also have to replicate this as faithfully as possible in the simulations. To show you how we can improve the performance in these scenarios, we trained SpatialNet, which is a neural network for multi-channel devices. And you can see here on the left side that we have several microphones that go as input to the neural network. And each microphone records a mixture of several speakers. So they have overlapping speakers. In blue and orange, you can see the different speakers here. And in green, we see additional background noise that is also recorded by all microphones. And then the network outputs are enhanced speech signals, which is essentially now the clean enhanced signals for each individual speaker. And in this case, we trained the SpatialNet using a 6-channel subset of the eigenmic. Of course, nobody would use an eigenmic for speech enhancement, but we still think it's a good kind of proxy for a smart speaker because it's a rigid body. It has several microphones on top of it, so it is pretty similar. And we use a subset of 6 microphones where we try to have one in the front, in the back, left, right, and top and down. Once again, we have 2 datasets that we compare. The first dataset was simulated with the Treble SDK, and we use also our advanced device rendering capabilities there, where we simulate 16th order ambisonics and then render these spatial IRs to the eigenmic device in different orientations. The second dataset uses the GPU RIR toolbox, and it uses an open microphone array, which is pretty standard in these open toolboxes. And once again, both datasets cover roughly the same range of T30 values and room dimensions. And also here, we are interested in the real-world performance, so we evaluate the dataset again on measured data. And what we're doing here is we actually have one dataset of noisy eigenmic recordings, and we feed that one time through the trained spatial net with treble data, one time through the spatial net that was trained with GPU RIR data, and then we get two different streams of enhanced outputs. And both of these streams are fed to the same automatic speech recognition system, and then we get different word error rates out, which tell us how many mistakes did the speech recognition system make. And then in the end, we can compare these two different word error rates. And that's what we see here. And we found in our study that using treble data, we get up to 30% lower median word error rates than using GPU RIR data through the improved speech enhancement that we have in the spatial net. And we see here the different overlap conditions. So there's always at least two speakers in the data set, but they are between 0% overlap and 40% overlap. And for larger overlaps, we also get a bigger difference in the word error rate improvement, which makes also some sense because we have additional information about the source receiver configuration if we use advanced simulations. And the datasets that give this performance increase are now available through our website. We have a dedicated page for it, so please fill out the form and we will get in touch with you. Now finally, I still want to talk about the binaural speech distance estimation and localization network. And in this case, we train this network here on the right side. And this works by feeding in two microphone channels on the left and right ear. And we get the direction of arrival of a speaker and the distance of a speaker as outputs. And we saw, once again evaluated on measured data, that if we use treble data, we get better performance compared this time to Pyroom acoustics and to the image source model dataset that was provided by the authors of the paper. And we see, for example, for the localization error, we get up to 15 degree smaller localization errors than the other models. And for the distance estimation, we get around half of the distance error that we get from the models trained with the other datasets. So finally, I still want to mention very briefly one study that we made where we used room acoustic simulations as an alternative for measurements in audio algorithm evaluation. And if you're interested in that, our findings have been published in a peer-reviewed journal called IEEE Access that you can find linked here. So please give it a read if you want to find out how to use our simulations for evaluation as well. Thank you.
Hi there, my name is Tim. I am co-founder and head of machine learning at ai-coustics. Voice is crossing a threshold. It is now a core infrastructure. And unlike text or UI, voice offers no retries. When a system mishears once, trust is lost immediately. ai-coustics exists to fix the part of voice AI that usually breaks first, audio reliability. We build the audio intelligence layer between real-world sound and machine understanding. Our SDK turns raw, unpredictable audio into stable, machine-ready input for voice AI systems running directly on-device with a sub-40 millisecond latency. Today, I will explain how we at ai-coustics help making sure that voice agents work reliably in production and how we partnered with Treble to build specialized semi-synthetic training data sets for our models. Most voice agents use a cascade of AI models, usually a speech-to-text model turning audio into text, a prompted LLM to process the information and generate written answers, and a text-to-speech system reading out the LLM-generated text. And they work great in demos and POCs. Voice agents work great when they're tested under lab conditions, in isolated environments with good hardware and by people who know how the system works. But things can quickly fall apart in production. The reason is that the real world is messy, and even modern SCT APIs are surprisingly sensitive to degraded audio input. This might be the result of low-cost hardware, transmission artifacts, or noisy environments. One of the biggest problems our customers complain about is interferent background speakers that break conversation flow and confuse the voice agent system. Here's an example of such a failed call. The voice activity detection is falsely triggered and the STT transcribes the background speech. This leaves the agent confused, the conversation flow is gone, and the user is annoyed.
Yes, definitely. I remember thinking about getting a solar system for my home, so I'm definitely very much interested. In it, yes.
That's great to hear. Thank you for confirming. To make sure we can provide the best advice and solutions for you, I'll just ask a few quick questions.
They had like 2 different pasta dishes, separated.
Yes, I'm listening. Michelle, are you good? Did someone kill you? I hope you live. Michelle?
That's why we built Quail Voice Focus. It solves the failure mode we just witnessed and more. It blocks interfering secondary speakers, as well as sound from media devices such as TVs and radios playing in the background. It cancels echo and of course also performs denoising and heals other common degradations like clipping and codec artifacts. Here's an example of Quail Voice Focus in action. As you can hear and see, both the VAD and SCT signals are fixed when pre-processing the audio with Voice Focus.
Stefan, you would usually look after that, right?
Yeah, like sports, like say you're at the football game, and then you take that noise, you can record
Perfect.
the voice. And then
Okay, thanks everyone. Stefan, you would usually look after that, right? Perfect. Okay, thanks everyone.
So how did we do it? Well, behind every great model, there's an even greater data set. At the core of our data engineering is our audio augmentation pipeline. It allows us to mimic real-world audio signal chains and create hyper-realistic synthetic training data sets. For the development of Voice Focus, the Treble SDK was an important piece of the puzzle. It enabled us to create thousands of artificial scenes where we could virtually place media devices and background speakers relative to the main speaker to simulate real-world conditions. The result is a dataset and a corresponding model which solves the interfering speaker problem and makes voice agents more reliable in production. This also materializes in quantitative benchmarks. Voice Focus reliably reduces word error rates across STT providers by minimizing insertions from background speech while not suppressing the main speaker. Voice Focus and our other models are available through our lightweight SDK. It only takes a few minutes to integrate into your stack. We provide language wrappers for Python, Rust, Node.js, C++, C, and WebAssembly. Just go to our developer portal, generate an SDK key, and follow the quick start guide. We also integrate in the PipeCat and LiveKit frameworks. And by the way, we are growing our team in Berlin. Please reach out if you're interested. Thank you for watching.
Hi everyone, my name's Sarabeth Mullins. I'm a senior simulation specialist here at Treble Technologies, and I'm going to take a couple minutes to discuss an upcoming beta feature, which I'm personally quite excited about, which is our audio scene generator. So we've been talking a lot about the use of the Treble SDK as a part of a product development workflow, and it's important always to keep in mind that the products that we design, the algorithms that we develop, are going to be more often than not deployed into a complex acoustic environment rather than a simplistic one. So, of course, if you want to evaluate the device that you're designing or have more rigorous data to develop your algorithms with, there's sort of been 2 ways, traditionally speaking, to go about developing that data. So the first one is the fully analog method, where you go out into the real world and you measure those environments yourself, which can be very expensive, be very time and labor demanding, and you don't have as much control over the actual signals that you're recording or precise information about what you've recorded in the same way that you might if you simulate this complex scene. So on the traditional way of simulating the complex scene, of course, you can take your audio files and your impulse responses, but this might end up being a multi-stage process with multiple computer programs involved, multiple repositories, and assembling the data into a usable form with all of the information required can be a bit of a faff and can also be a little bit difficult in order to keep a handle on all of the information required. So the Treble audio scene generator is our attempt to help solve this problem, so we don't have to continuously reinvent the wheel when it comes to this particular issue. As you can see on this slide, the core of the scene generator are two types of collections. The first collection is an audio collection, which is the dry audio signals you'll use inside the creation of this dataset. And these can be sourced from a directory with WAV files on your local disk. This could be internal Parquet files. You could be pulling something open source, such as from Hugging Face. As long as you have the audio, you're good to go. And then on the other side of things is the impulse response collection. And this IR collection is a Treble object, which we've talked about a little bit already. This IR collection likewise can be sourced from a number of places. You can create and simulate the rooms yourself if you want complete control over the acoustic environment. You can pull an IR collection that was prepared for you by someone who specializes in acoustic simulations within your organizations, or of course you can purchase a data set from us directly. But as long as you have that dry signal and that IR collection, you can combine them in our scene generator using a set of metadata with conversation rules, with device-specific details and listener rules. And in that scene generator, we handle all of the issues of sequencing, of preserving the information about what is being said when, where, and by whom, and where they are saying it with relationship to the device that is listening. So that was a theoretical walkthrough, but of course it's interesting to see what this looks like in practice. I have here a pre-rendered audio scene that we've created to show the classical cocktail party effect. In this scene, we have a complete bar with many human speakers inside, as well as a loudspeaker system in the corners. And we have a receiver here who is facing directly towards the back of the bar. And we have a target speech signal, which is here in the left ear of our device. If we were to render this traditionally using a simple impulse response and signal, it would sound something like this.
The increase of rents is due to two causes.
Of course, that's fine if you're looking for a clean signal oralized inside an acoustic environment, but if you want to hear something a bit more complex, we can simply unsolo this track and listen to the entire scene.
The increase of rents is due to two causes.
And it was over these girls that Grace proposed.
So the way we create this is relatively simple. The very first thing we do is we fetch an IR collection. In this case, we're fetching it from our data set. And we're taking a data set of 20,000 impulse responses in order to use it in our scene generation. We're also going to grab two audio data sets, one from Hugging Face. We're going to load the LibreSpeech data set. And the second one is going to be a local set of music files for use in the background. Once we have loaded the audio data set, we will then go ahead and create our set of scene rules and source group rules, which will govern things such as the overall volume range allowed in the scene, whether or not our speakers within the scene are going to be polite and take turns talking, or if they're going to talk over each other. As you can see, we have a number of presets. And once we have defined all of these, we are then going to grab a device. In this case, it's going to be a Kemar dummy head. We're going to add some noise to the channels to imitate the same measurement noise that you would expect to see in a realistic scene. And then we're going to define an orientation of the listener. Once we've done that, we can generate the scene and plot it and see the following. Now, I've actually been a little bit cheeky here because I've rendered this using the advanced features, which will be coming soon, released as the feature becomes mature. But here you can see that we actually have a source that is moving, And you'll notice one additional thing as we listen, which is that the receiver orientation is going to automatically update as a function of who is talking close to it. So let's go ahead and listen.
Overheard Chester tell Miss Kane the other day, and that his followers would lose a throne.
Of course, this all is very cool, but it's less useful to be able to generate these one at a time. So we have also included the ability to generate these in bulk. In this instance, I'm going to be creating 250 scenes. And as you can see, we're already moving quite quickly through the possible combinations within this room. It will, of course, take a few seconds because we are randomly and stochastically assigning these various properties following the rules. But once we're done, we're going to have a complete set of metadata files that show the individual information for each of the scenes that we've generated. As you can see here, we're looking at sort of the top-level summary of all of this information. And at this point, we could either proceed to render these scenes directly into audio files and save them as outputs, or we can save these recipes into a Parquet file for later use. Thanks so much for your time and attention. I hope you enjoy the rest of the webinar.
Hello, my name is Yauheni. I'm simulation specialist from Jabra. Welcome to my short presentation. Today I'm going to talk a bit about our collaboration with Treble, which is going continuously, and we are quite happy about this. And in my talk today, I would like to say how was it started, how we use Treble as a tool to validate our room acoustic simulation and measurements. And so further, I will say also how we use Treble for testing and prototyping our products and algorithms. And in conclusion, I will say also about our future perspective for collaboration with Treble. For the beginning of our collaboration, we decided to test Treble as a new tool for acoustic simulation. So since Treble provides a unique hybrid method, we can combine geometrical acoustics and wave acoustics in one software. So reasonably will be to test it against measurements and to make first conclusion about how can we trust Treble for our work. For the first test case, we used our room. Here we labeled room A, where we put a loudspeaker and 3 microphones. During our measurements and simulation, we rotated loudspeaker and also changed its positions to have a complex data set to make first conclusion. Moreover, our room was decorated with flex panels that can be open, closed, in order to mimic different acoustic conditions. Also, it's a good thing that we decided to try and to validate material builder from Treble to have material models for flex panels and to see how can it be compared against measurements. So here I would like to show some first results, and for 2 cases when all panels were closed and all panels were open. For closed panels case, we compared 2 room impulse responses from loudspeaker that is positioned directly towards receiver 1. And also here, I zoomed in first 20 milliseconds of this room impulse response. So you can see that Treble can capture quite well direct sound. A little mismatch can be explained between some different positions of loudspeaker during measurements, and also Treble captures quite well some reflective sounds. Also, as a parameter for comparison, for example, here T20, that we can see that in terms of absolute values we are quite good agreement, and also in terms of trends we can see that all trends are there on this plot. For open panels, we did the same. We plotted 2 room impulse responses against each other. The mean first 30 seconds of this room impulse responses, we can see that again that we capture very well direct sound, little mismatches between reflective sounds, so it can be explained with different complex geometry of open panels, but we are still happy with the results. It's more than nice. And also in terms of T20, for example, that values from my point of view are quite in good agreement. So we can use Treble further for our next test room. For our next room, here labeled room B, it's a room without flex panels, but the aim here was to test material library from Treble. We know exact material for walls and floor. So we decided to test how material model from Trebles are good to capture measurement results. And for 3 microphones, I plotted here T20 parameters. You can see that the room was quite reverberant, but Treble did very good job in terms of results match with the measurements one. So we decided to do a final test for Treble to test one of our product in a real meeting room scenario. And for simulation and for measurements, we took one room and use the RTF approach for device simulations. That means we can simulate actual device once in free field condition and then inject this device in any rooms, change its position, orientation for different room scenarios. And for simulations also we injected different number of mannequins. And to add more realism, we used model from Treble based on boundary velocity mouse acoustic source to real mimic human speech. Also, we use table and some planes that mimic laptops in real measurement routine. Also tested different scenarios. And in order not to get bored, I plotted a scenario when from the start, we plotted room impulse responses when we have only one speaker in a room with a laptop, and also our product video bar was at another end of the table. So just if you look at the results, they are very, very nice, and we are happy to see that it's a very good agreement between simulation and measurements. And finally, I would like to say that for our prototyping and testing for our new products, we're using Treble. It's a platform for virtual experiments. And for example, to develop microphone array for beamforming and for other types of algorithm, where we can easily generate rooms with different RT60 parameters, change device position where we want, and also to use different types and position of acoustic sources to mimic real human speech, different noise distractors, and to make sweep over all coordinates, and also put whatever number of microphones what we want to test. So, and also to do simulation with device and with floating microphones without devices in order to make conclusions for performance of our microphone array design. So unfortunately, due to confidential politics, I cannot say so many details yet, but maybe I hope for future webinars I can share more interesting results or in terms of our joint publication. As a conclusion, I would like to say that a hybrid method implemented in Treble demonstrates very good agreement with measurement results, and we are still very happy to use it as a platform for our virtual testing and prototyping. Also, we are quite happy with different types of simulations approach that Treble provides for us. And our current goal in collaboration with Treble to use Treble as a tool for synthetic data generation for designing and improving our different algorithms for our future products. I would like to thank you for your attention.
All right, that's it for today's presentations. I hope the content was insightful and valuable for all of you. Thank you so much to all the speakers, both the Treble team and the great guest speakers that we had. If you're interested in exploring this further in any which way, don't hesitate to reach out to our team, explore our website, and so on. But without further ado, I think we just head into the Q&A session. Thanks.